Some people go to the sea to escape the busy times in the city and have some peace and quiet. For me, the place where rivers meet the sea is actually quite exciting because of lots of things are happening there. Although sometimes you would have to look at this through the eyes of a geologist, which means that the millions and millions of years are speeding by in a matter of seconds. And then it's really exciting. Anyway, I am Maarten Kleinhans. I'm going to talk about estuaries and deltas and how to simulate these things in experiments that even you can do in your own backyard. I will talk about phenomena in nature, landscapes in nature, not only on Earth but also on planet Mars. And I will talk about experiments, how to simulate them. And some of them will be so simple that you can actually do that yourself. But make no mistake, some of these very simple experiments were really insightful and have been published only recently in scientific journals because no one had thought of doing them before that. So we'll talk about how to do experiments, how to set them up, and then what to measure in order to get a feeling for what happens beyond your own impression. You can measure the slope, for example, or change. You can do time-lapse images with a camera or telephone. You can measure flow velocity by dumping in tracers or colored stuff. And we can look at the strata that it makes, and I'll show what that means later on. So let's first go to planet Mars. Because planet Mars is showing lots of signs of things that are really rivers. All these tiny channels that you see here go into the biggest canyon in the solar system, the Valles Marineris. And we know for a number of reasons that it was water that made these valleys. And lots of the reasons are visible on the surface because of what the landscape looks like, but also the water itself has been found. One such indication that this is really water is that impact crater, that little circle you see just below the middle. It has a sort of apron around it, and unlike ones on the moon where you have lots of rocks on the surface, this one looks as if it splashed down into a watery soil, which is actually true. So water came out of the high rim in the south and in the north, and it flowed down into the deep canyon, kilometers deep, and that is what incised these little valleys here. In many places on Mars you find these things, and in fact also on Earth. Here you see an elevation map of a place on Mars where we have a little delta. So from the bottom left, water came out of the ground, seeped downhill and carved out a big channel. And the sediment, the sand, the gravel, the mud, whatever kind of sediment, it collected further downstream on the top right in the form of a delta. You see a semicircular shape, and that is being deposited in standing water. And I know that because of its steep slope. And we even see the culprit, the smoking gun. There was ground ice on Mars. There still is a lot of ground ice on Mars, and in this case it melted because there is a fissure volcano. That warty thing, that elongated, warty, ugly thing there is a volcano, and that created so much heat that the water melted and created this beautiful valley and delta. If you were to take a look on the ground, which robots are doing as we speak on Mars, you would see something like this. For example, right? Gravel. What you see here is gravel that you can find in many places in England, but also on Mars. This is the stuff that comes down from the mountains when the mountains wear down and then forms fan-shaped features that we can call deltas. So what we're seeing here, in a nutshell, is that we have sources of water. That water brings sediment, and that comes from eroding the mountains, and then that moves down a river, and that's the path, and then it ends up in a sink, and that can be a delta, which is building up from the coast. It can also be an estuary, and an estuary is a place where there's not really a delta building out, but the river meets the sea, and it's actually a valley that is being filled. England had lots of estuaries, so it's something you will probably have seen at some time in your holidays, or maybe you're even living on it. So estuaries are very much formed by the tides, the ebb and flood currents, and also by the waves coming in from the sea. Now, how do we investigate all this in the earth sciences? Here we go again. That the sand is taken out with the water, and then the valleys carve themselves uphill as sand is being removed. And this is exactly what many of those valleys on planet Mars look like. The soil has collapsed, the water takes out the sand, and you get these theater-headed valleys that are quite common on Mars. And then on the downstream end, that sediment is taken away, and it may end up in a big valley, or it may create a delta, like we see here. The right one is a real delta on Mars, where you can see remnants of shorelines. It's a fan-shaped feature in standing water, and on the left we have an experiment. We made a crater in the lab, an impact crater, a sort of circular basin in this case. We let water flow into it, and this is what happened. As the lake flooded, the delta built out, but the lake flooded faster than the delta could build out, so we see all these reducing delta lobes on top of each other, reducing in size, and that's what happened in this particular crater delta. We see a lot of those things on Mars. Here's that other case that I showed earlier in the elevation map again with the fissure volcano. This one had lots of time to build out, and then it really became a delta as we know it from the classic Greek letter delta from the Nile Delta. And this is a delta that you can also make quite easily in any sandbox on a schoolyard. In fact, it has happened. This girl here is measuring the slope of such a delta which formed in the schoolyard after a fair shower of rain. And you can see how the delta has built out when there was still water by distributing the sand in a sort of fan-shaped feature. It looks remarkably similar to the big deltas on the planet. This is the Nile Delta in Egypt, and we're looking south here, and you can see where the river water is coming. That's where it's green, while the rest of the land is brown. These deltas occur in many places. Here you see very nice examples, and this is a nice example of how you can investigate these things in nature. We have two deltas here. The one on the left with colors overlaying for elevation, and it's really fan-shaped, and you can see the tentacles, the tentacle-like features actually building out the delta. On the right hand, however, we have a delta with very little sediment. So there we see a little bit of sand around the meandering rivers, but you also see there's lots of green and brown around it, and that is actually peat in the landscape. So it's not sediment, it's plants, dead plants piling up on top of each other. The yellow triangles, by the way, are Inca temples. The Incas built their temples on the higher sandy landscapes. So how can we investigate nature? How can we investigate source-to-sink systems, deltas, living landscapes, that sort of thing? We have a number of ways of doing this. Ideally, you would change something in nature to try and understand what the response is of such a change. And we are doing that, but in doing so, we change nature, so we don't really know what would have happened if we hadn't interfered in nature. So this is a difficult problem for scientists, because we really would like to know what's doing the change. Also, it's dangerous to do this. It's going to cause problems. In fact, the old saying by Lord Bacon was, you would like to twist the lion's tail, you would like to twist the lion's tail to see what the lion will do in response, and you would like to do the same thing to a delta, twist the river's tail if you like, but it's only allowed for other lions, and then only in the mating season. So instead, we'll have to make do with our hypotheses and conceptual models, but you can see it's risky to do that. You can see that there is definitely lion aspects to our ideas about it, but there is also human bias. For example, that lack of hair on the top of the head of the lion is my situation, like the glasses. I would like to stress I do not have a tattoo, but this lion is clearly twisting his own tail. Of course, we can also do numerical modeling, and you'll see weather models every night on television that predict the weather for you, and they contain mathematics and physics and all that, but they have their own dangers. Models do exactly as we tell them. It doesn't mean that they necessarily do what nature does. Of course, we make them as well as we can, but they're not always the best tool. They only do what we put into the model. And then there's a third way of investigating nature. We can try to simulate nature or find smaller bits at smaller scales, and then things go much faster and much less dangerous. So we can twist a cat's tail. And that is what we're going to do with the experiments. So you can see that what Earth scientists do, and many other kinds of scientists do, is actually in all kinds of ways difficult. So we use as many different methods as we can to unravel better what happens in nature. Experiments are relatively simple. You can see here I'm working with primary school children, and they can do it too. We have a simple small sandbox. There's water coming in, water going out, and there's sand in it, and that's it. So it's doable. And then we can start investigating what's happening. That sounds really magical, right? Investigating what's happening. And how do we do that precisely? A lot of people in the world don't really understand the process of science, but it's actually quite a simple process, especially if we do experiments. I'll come back to that later on. So one thing I hope to accomplish is that science loses its magic. Of course, there are all kinds of magical things going on in science that look really magic. For example, you see the magicians with all sorts of gowns, and you see the professors with all sorts of gowns. In this case, it's me in my inaugural lecture. However, this is not what science is about. Science is about messing, playing, finding out what causes and effects there are in the world. And one way of doing that is doing experiments, because nature is a big mess. If you would like to try and find out how it works, you're looking at the right side of this image. Whereas if you can actually make nature in some sort of way, then you can really unravel much better what's causing what. Now, why do we understand all these living landscapes? This was the introduction, and now I need to give the rationale. Why am I so interested in this kind of landscape? In the first place, I think they're beautiful. They're fantastic patterns in nature. I love it out there. I love nature. I love landscapes. I love geological processes. I like Mars. I wouldn't want to go there, by the way. It's a really horrible place, but it's nice to look at. But there is another reason. And that reason is that we are living in these landscapes. 1/3 of the world's population is living in coastal plains and deltas. And at the same time, we are causing climate change, and we will have sea level rise in the next century. And that means trouble for these low-lying landscapes. Let me show you what happened in the Netherlands. All these gaps in the north of the country were made when the sea breached the dikes and then went inland. But the fact is, this only happened after we made dikes. Before there were dikes, before, say, the late Middle Ages, the land flooded regularly, but not badly. It flooded regularly, brought in new sediment, let the plants grow, and as such the land rose with the sea. So that was actually what kept the living landscape alive. And then we built dikes, and then the land began to subside. That means it began to compact under its own weight, and there was no new sediment coming in. The land had always compacted under its own weight, in fact, but since there was no longer any new sediment coming in and the plants were taken off because we wanted to do agriculture, it began to go down. The sea stayed put and then breached the dikes, and then we had floods. And you can still see the scars in the landscape. The light brown bits are water. This is where we still have water, what used to be land. The most famous example in the Netherlands is a big flood, the St. Elizabeth flood in 1421. And you all know probably for England there are stories too of big floods. There's a famous one, of course, 1953, but there have been many floods before that. This flood has been painted literally on paintings and also figuratively in writing as a natural disaster. The dikes breached, it came in as a big flood wave, it destroyed the landscape, it was punishment of God, all kinds of stories went about. But the simple fact was, this was one of those landscapes 300 years after we made the main dikes that went down. literally. It compacted by over a meter or two in the time since the dikes had been built, because there was no new sediment coming in, and people were dewatering the landscape to do agriculture. So what really happened is that the dikes breached, and the land went dry again during ebb, and during flooded again, etc. People had actually time to move. This painting shows you that the people actually had time to pack the stuff, move out of the area, because they could no longer defend the area and repair the dikes. Nevertheless, they had time to take down church towers, which were expensive, they had stone in it, and they were able to take out their stuff and their animals, or at least most of them. You do see the occasional dead cow and dead person floating into the water, but most of it was taken out. They had time to move. And then after 1421, the River Rhine, which is a fairly big river, dived into this low-lying area and built out this inland delta. Here you see again a fan-shaped feature that's really a delta, that's inland. And on the left you see the city that depended on the wheat that was grown in this area. And this was one of the two cities that was fighting at that time in our civil war to become the main capital of the Netherlands. You all know that the capital of the Netherlands is Amsterdam, and it's because of this flood. Otherwise it could have been Dordrecht. But who's heard of Dordrecht now? So there's a myth around in the world. The Dutch made Holland. God created the world, but the Dutch made Holland themselves. And then revised history actually. This is not true. This is rubbish. What in fact happened was the Dutch made Holland drown. They built dikes all over the place. They even carved away the peat, the dead plants, because they wanted fuel and they wanted to take out the sea salt, because then they had salt. This is what science is all about. It's not about becoming popular or building a body of known facts. This is Terry Pratchett saying what we all know as scientists. Science is a method for asking questions and then investigating that. And it doesn't make me feel good that the Netherlands actually went down because of our own doing, but that's what happened. Worse, it's still happening. This is a map of most of the Netherlands, and the browner, darker the color, the faster the soil is going down. So the dark brown colors are going down by about a meter per century, right? A meter per century is going down. The sea level is not rising much yet. It will rise much faster next century, but it's not rising much yet. But the land is already going down a meter per century. That means that we have relative sea level rise, or land level lowering if you like. And the reasons for this are our groundwater management, the digging away of peat, that's the deepest areas actually, and there's no renewed sedimentation. This shows a very important thing. A delta, a living landscape, it's not a thing that you can use and stand on. It's a process. And if you kill the process, the thing is going to decay. And that's also true for large parts of England, United States, Canada, Northern, the Latin America, the tropics, China, all over the world, this thing is happening. So this is the situation. After the last glacial, when the glaciers, the polar caps melted, mostly that is, the sea level went up. So here you see a time series. The vertical axis is meters above sea level at present, and the horizontal axis is thousands of years. So since about 10,000 years ago, the sea level rose over 25 meters. In the last, say 2,000 years, it only rose very slowly. It only rose a few meters. This is the situation. So basically we've had nearly constant sea level for the past thousands of years, and this is when deltas began to build out, and that's the stuff we're living on. But the future projections are not so very happy. Here you see the climate predictions for the coming 5 centuries, and of course they are very uncertain. I don't care about the uncertainty. What's really uncertain is how humans are going to deal with it, because the red line is what happens if we continue doing what we do now. The blue line is what happens if we stick to the Treaty of Paris, the Climate Treaty of Paris, and the black line is if we really wanted to keep the world the way it is, we need to stop putting out CO2 and other greenhouse gases. Now, this plot, scary as it is also going up for more than 15 meters in the worst case scenario that we are doing now actually. It only has 500 years on the horizontal axis, so let's compress it to have the same horizontal time axis as the other plot and then get this. And this is really the thing, right? Sea level is going to rise so fast that we really need to worry whether the land level is going to keep up with it, even in natural deltas. Worse, we are lowering the land. That's this arrow that we should add to it. So you see, we have a problem. Everyone who's living in the coast has a problem. This is the Netherlands at the moment. If you were to have no dikes, half of it would be already flooded by the sea. So that leads to the question whether the Dutch are really sticking their heads into the sand like an ostrich, right? This is what we are worried about as earth scientists. So if we stick our heads in the sand, then we have a problem because in the next century our grandchildren will need to get their heads out of the water. We're not going to be able to keep up with the changes that we have caused, despite the rhetoric that the Dutch are so terribly good at water management and building dikes and dams. You don't believe it. But there is a plan B. Some areas in the country have lots of sediment around, moving around by tidal currents, by the waves, by the rivers. And then we can make use of that to build the land. You see that early in the Holocene, when the sea level went up so fast, the land drowned, as you can see in this cartoon. But then, as the sea level rose slower, the peat was able to build out, that's the brown color, partly through development of natural vegetation, which is the green color, and also due to the delivery of sand and mud from the big river, which in our case is the Rhine or the Ems or the Scheldt, and in your case is the Thames and the Humber and the whatnot. Lots of rivers we have. So if sea level rise goes slow enough, we can maybe do land level rise and keep up with sea level. And that means we need to stick to the Paris Treaty. There's more. Let's look at this bit of land here. This is a beautiful landscape in Wales. You're looking at the Dovey estuary. And you can see it's an estuary because of the funny shapes that clearly show that the flood comes in every day and carves these channels and floods the sand. And the thing is, we have a drowning landscape here, right? With the sea level rise and the rising sea level. But there's mountains and sediment is coming out of the mountains. And we have plants growing there that can capture the sediment. So you can see what I'm going to say now. Can't we use that sediment to grow this landscape up with sea level rise? That's the question. And that is why I am studying living landscape. This is the sort of thing that I would like to know. How these beautiful landscapes come about and how we are going to meet the challenges of this in the next century. Of course, at present there's a dike here, so it is going to be necessary in places to remove the dikes, and you can hear the protests already of people clamoring that this is dangerous, you're playing with people's lives, we're losing our land. Well, we're going to lose a lot more land if we don't do this kind of thing. And in the Netherlands we have great problems with that actually. Here you see a former estuary. This is no longer a living landscape. You're looking at Rotterdam, the port of Rotterdam. It's a main port, it's one of the biggest ports on the world. It's very important for the economy of the Netherlands, and everywhere you see this green speckly thing on the satellite image, that's buildings. It's city. This landscape is no longer living at all, that is not naturally. And this overlain of what it used to be in the 19th century, over a century ago. And you can see it was really an estuary with islands. And if you zoomed in on the map, you would find salt marsh and you would find mud flats. In short, a natural landscape. So in places, we're going to have to deal with dams and dikes. We can't do anything else. But maybe in other places we can do better. So let's do experiments to try and find out how these landscapes work, and then it's quite likely that at some point that work will actually be useful and we can put it to use in our real landscapes. But we want to learn more now about how the landscapes form. That means mechanisms, but also the effects of life sitting on the landscape and how landscapes change after we change conditions. For example, the amount of water that comes down from the rivers, or the sea level, or maybe even temperature. In other words, climate change. And we would like to see what happens if we mess it up. And we can do that in a sandbox. Remember, it's the cat. We can twist its tail without the danger of being eaten by most cats. So, experiments really is a piece of cake. Here you see kids playing with two rivers, and they invented one of the more important laws in our field, which has something to do with the width of rivers. And he also breached dikes, which you can see in the bottom photographs. It's not so difficult. So how do we do that? We need to feed water and sand, really. That's all there is to it. On the left you see a beautiful delta on top on Earth. It's in Canada, I think, the Horton Delta. And on the right you see a beautiful delta on planet Mars in a photograph. And on the bottom left we have an experiment, an elevation map. And all the dimensions there are millimeters. So it's really a small delta. It's actually only a few meters. And it simulated the natural delta in a number of important ways. And likewise on the right, we also have a delta formed in the laboratory. You see the elevation map again. And you can see there's all sorts of similarities, in particular those terraces, those lobes of deltas on top of each other. And we know it's an experiment because you can see the shovel down there in the elevation map. This is that beautiful delta again on Mars. We can do this. Those are the experiments that created the sand expulsion by groundwater outflow. We can do this in the laboratory quite easily. In fact, you can do it on the beach. The essentials are, remember the source to sink story, water needs to go in and needs to go out. So we can use a watering can if we have a limited amount of water. You can use the tap. It's a bit of a waste of water though. So if you have a garden pond pump, it would be even better because then we can pump away the water from the bottom end and put that up on the upstream end in the river again and circulate the water. We would have a hydrological cycle in the laboratory. If you want groundwater outflow, just put the source under the ground. That means you take the garden hose, you put it in the ground and then wait and see what happens. That's all there is to it. The other thing is we need the sand. You need to screed a bit of a plane or and then feed water over it. And you can feed sand by hand from the water inlet. What happens if you don't do that? If you don't feed sand? It's a nice thought, right? Let's just let the river carry away the sand and see what happens. I'm not going to give the answer. It's quite simple to find out what happens. One or two hints. Coarse sand and poorly sorted sand is better. The dirtier the better, really. The size of the sand doesn't really matter. That it moves is all that matters, and I'm going to talk about that scale problem later. The other thing to realize is that rivers are nearly flat. A river gradient is really a slope that's small. It's a few degrees at best. River plains and fluvial plains and coastal plains are really flattish, not like mountains. So what happens if you feed no sand from upstream? And in fact, the hint is already in this photograph. You get erosion. The channel gets deeper and deeper. And what happens if you feed a lot of sand? Well, try it out. And what happens near the sea? Well, that's what you also see in this picture. You get a delta. This is what it would look like in nature. This beautiful delta here, multiple channels. There's trees in the background which also do something to the delta. What happens if you grow vegetation on your delta? Well, you can do that. You can go to the grocery store or to the garden shop, buy seeds from a small plant, preferably a weed, and grow them in a few days on top of your sandbox and wait and see what happens. There's an interesting feature that's the easiest to make. The fluvial fan. It's basically a delta, but then without the sea. It happens when you overfeed a river with sand. The river gets more sand than it can transport, so it dumps the sand, it doesn't transport it, and you build a steeper feature. And you can see one in the middle of the yellow circle, and of course this is nearly the entire Latin American continent, so you can see what an enormous feature that is. And if you have Google Earth or Google Maps, you can see them all over the planet. So let's zoom in a bit. What you see here is a fan-shaped feature. The river is coming from the right, and it's spreading out in the middle over a wider plain, and it's spreading out by displacing its course every now and then. And the blackish stuff is actually the floodplain, the place where it floods and where there's waterlogged area, and this is where it deposits mud and sand, and that's how it builds out that fan. Now this is a piece of cake in the laboratory. Here's a couple of beautiful pictures from this feature in a complicated laboratory experiment, but the simplest fan is simple. On the top left you see the fluvial fan again. In the middle at the top you see our fan. And this is a fan that was basically done by feeding water and sand on a flat sandy floor. That's all. And we feed more sand than the river can eat, so it builds up a fan. But the trick here was not only to build out to feed it with sand, but also feed it with crushed nutshell and coal. And if you don't have that kind of material, you can use any other kind of dirt. You can try mud. You can also try the stuff that comes out of the coffee machine when it is finished making coffee of it. It's really beautiful in experiments. And then if you look at the bottom pictures, you see what landscapes it makes. We put a little bit of blue dye in the water, so it's better for visualization. You can see where the channel goes, and then it builds out bars. And on top of the sandy bars, it puts the lighter stuff, the nutshell and the coal. And this is how it builds the higher landscapes with fertile soils that were the places where civilizations formed. The Harappa civilization in India, of course, there's the Nile Valley. With the Nile Valley civilization, there's the Euphrates and the Tigris rivers where civilizations started and the first cities were built. All that is because of the fertile soil, which we here simulate with something that's lighter than sand, namely nutshell or coal or coffee material. And then if you were to carve a trench through one of these bars, you would see layering. Because of the natural displacing dynamics of the river, you sometimes see layers of muddy stuff and other times layers of sandy stuff. So if you went to any outcrop of rock, like you see here in the top right, this is what you would see: layers of fine stuff and layers of coarse stuff. So that's all right. Fans is easy, deltas is easy. Now what about tides and waves? That is actually more difficult. While that is, waves are fairly easy. You can flap a bar of wood or a big ruler in the water and you have waves, and you can do lots of fun experiments with that. But what about tides? Tides were a challenge. They have been a challenge for the past 130 years. Because the tides in the sea are water going up and down twice a day, because of the attraction of the sun and the moon, the ebb and the flood. But of course, when it gets near to the land and near to the estuary, that water that goes up into the sea is then driving an ebb current into the a flood current into the estuary. And when the sea goes down again, you get an ebb current out of the estuary. So the essence for what happens in estuaries is actually horizontal currents. Now, people tried to make that in the laboratory, making the sea go up and down by pumping, and then try and see whether it caused tidal currents. And that didn't work. Let me first show you what these landscapes look like. I'll show estuaries later, but this is what tidal landscapes look like in the north of the Netherlands, the Wadden Sea. On the right we have a true color photograph with a bit of exaggerated colors. You can see there's sandy beaches in the north, on the barrier islands. It's a bit like the Wash actually in England. And then we have sandy flats and muddy flats and a little bit of vegetation. And on the left image, the vegetation is colored red because it's a false color image with an infrared camera. But you see the same thing. It's like little fingers of channels all over the place and bars built up with sand and a little bit of mud on top of it. That's the Wadden Sea. What are these estuaries? I already showed the Dovey in Wales, where you can see sandbars and mud flats and vegetation in the bottom, and it's all being fed by a river. Estuaries are typically a bit more elongated than tidal basins because they are extended literally by the river. And in the bottom photographs there's another one. This one is in Australia. But I don't need to tell you to go to Australia. You can stay in England because you have about 100 estuaries in your country. So here is the first experiment on estuaries by an Englishman, a very famous one, Osborne Reynolds, Fellow of the Royal Society, and he did experiments around the 1880s to investigate urgent questions for the London Port Authority because they had problems with siltation in the Port of London. So what he did was make a big wooden basin. You can see top views and side views here, and he let the water go up and down. Well, he didn't do that himself, of course. He had an assistant who made the water go up and down tens of thousands of times in months and months of tedious work. Fortunately, we have pumps and machines for that nowadays. But anyway, we see a lot of things going on here, but they don't remotely look like an estuary. And the reason is that the sand that he did in this experiment hardly moved at all. The flows were simply not strong enough to move the sand. Because the sand is the same sand as we have in nature. We can scale down the estuary in size by a factor of 1,000 into a laboratory setup. We cannot scale down the sand 1,000 times. If we scale down the sand 1,000 times, then we end up with such fine particles that it becomes clay. Clay is cohesive, it sticks together, it doesn't move like sand, so it doesn't help. So the force of the water is much reduced in these experiments, but the sand is not. It cannot move the sand, and that is experiments. So what is that force of the flow? A little bit of basic physics here. What we do is try and calculate the force of the water body that is sliding on the riverbed. We call that the bed shear stress because it's a force per unit area. So let's look at the block of water here on a sloping sandbed. The block of water has a certain height, that's the water depth, and the force of that block of water on the sandy bed of the river is simply gravity, right? It's the mass of that water block, mass m times g, and g is gravitational acceleration of 9.8 meters per second squared, and that is causing the force of the water on the bed surface. We can also calculate the pressure here if we calculate that force per unit of area, and then it's becoming newtons per square meter or Pascal. Now, we're not interested in the pressure on the bed surface. We are only interested in the small component of the force parallel to the bed, because that is where the water slides along the bed and does a force parallel to the bed, and that is what moves the sand. And this is what we call the bed shear stress. The flow is shearing the sand. And we calculate that, of course, by decomposing the forces here to one perpendicular to the bed, which is not interesting, and one parallel to the bed. And that is the bed shear stress. It's the same rho, density of water, times G, times the water height, and then we have of course, the sign in it to compensate for the fact that we have a slope there. And that's the bed shear stress. These are really low numbers, actually. In low sloping rivers like the Thames or the Rhine, these are typically of the order of 1 to 10 newtons per square meter. That's how much that is we can do with the story of apples. Because the thing is, sand won't move below a certain shear stress. That's important to realize. Why not? Look at the left pile of apples. You can see, you can feel this is unstable. You only need to blink with your eyes, breathe on it, and it's already going to topple over. If sand is piled on top of each other like this, it would be so easy to move it. But of course it's not put on top of it like this. It's put on top of each other like you see in the right picture. They're piled on top of each other. Now, if you want to move that top apple, you need to tilt it. You need to topple it over the other two apples, and that means lifting the apple up. So it's really the problem here. If you want to move sand, you're fighting gravity. If it was just piled on top of each other, you would need very little force. But if you want to move one apple, you basically need to lift 1 Newton, because an apple is about 1 Newton. So this is the funny thing. Science and physics, they're everywhere around us. You can see them all over the place. And if you become a good and decent scientist like myself, well, you really become a sort of nerd. And life is much more beautiful, the world is much more interesting, because you see the science everywhere and you understand a lot more than most people do, unfortunately. By the way, there's a very easy way to try and remember this. Remember, there are famous apples here, right? And the apples that I've just shown you are also hopefully going to be famous now. Remember, apples are difficult to move, sand grains are difficult to move by flow, because they first need to be lifted up. And the force of the flow parallel to the bed is really low in lowland plains with low slopes. Because of that sign of the slope in it in the force calculation, you only have about 1 newtons per square meter. So try and lift up the sand then. So it didn't work in Osborne-Reynolds' tidal flume. And I did an invention to make it work. Let me take you through this complicated slide step by step. What you see here is the river water surface in blue on the top left and the sand bed in yellow. And typical water depth of rivers is between 2 and 20 meters, and they have a low slope in nature. But if you want to make them work in an analog model in an experiment, you make a steeper slope. That's it. The water depth is lower, you make the slope steeper, and then the same sand moves. You can move the same sand as in nature simply by making it steeper. And for rivers that works. That's why you have nice fluvial fans in experiments. It's all no problem at all. Estuaries is the problem. Here we have flood driving flows into the estuary and ebb driving and out again, and that makes the sand move. That's the middle top picture. But if you try the Osborne-Reynolds thingy by raising the water and dropping the water level in a laboratory flume, the sand hardly moves at all. Maybe it moves a little bit downslope. And the problem is the lack of water depth, because that is half of the story of the force of the water on the bed. And the other half is the slope, but you can't do much about the slope because you cannot make a very steep slope for the flood. So what I did was actually not raise the water level in the sea, but tilt my entire flume, my entire sand basin. I'm simply tilting it periodically. That does the trick. I took a photograph from the top when every time between the tilt you can see it's really going fast in the clock on the top right. And here you see a fantastic tidal basin like the Wadden Sea developing in lightweight sediment in a tilting basin. You see all the dynamics, right? And of course sometimes the camera breaks down, that's why you have the sudden jump, but you see the dynamics all the time. This is what we would like to have. This is what Reynolds could not accomplish because he forgot the idea that you can better tilt the flume. And then it becomes child's play to do this. Actually, here you see two high school students doing their final thesis in geography and physics, and they built a tilting flume, actually. And they simulated the estuary on where they are living, actually, on the banks of the estuary. So this is what it looks like. You can ignore the Nachtwacht painting by Rembrandt in the front. The thing is that the tidal tilting flume in the back is tilting, and you can see the water moving in and out. It's this big for real, but it also works in a smaller setup. The bottom of that big steel flume of mine is actually a bit like the bottom side of the giant water lily, because it had to be lightweight, because I'm tilting it all the time. But this was only a fun fact that's completely useless to you. So what am I doing here? This is that tidal flume. You can look at the nice movie, how it was built and how it works. But the thing is, we are really feeding simply in water from the river with a bit of crushed walnut in it, and seeds if we like plants in it. And at the sea we can do a constant water level, but the whole flume tilts, so the flow goes still in and out of the estuary. And we can also flap a paddle and then have waves. The thing here is that the scaling is about 1 in 1,000 in space and time, because I made the sand as mobile as it is in nature. I compensated for the lack of water by having a steeper slope, and that was all was needed. So here you see an animation of images on top and a computer model on the bottom of the water flow moving in and out of one of our estuaries. The seaward end is on the right, and you see that the estuary becomes narrower and narrower and is basically a river if you go upstream to the left. So we go back and forth with the flow, even though the flume is moving up and down, or in Osborne Reynolds' case, the sea level is going up and down. Now, we added nuts, not crushed nutshell actually, because it creates mud flats. The mud is lightweight, it ends up on top, and you get these beautiful mud flats like you also see in, for example, the Humber. And what I'm really doing here is investigating like a scientist. I'm going to explain to you the empirical cycle, which you will recognize. Let's begin with the question. What's the difference between an estuary with and without mud? What's the difference in morphology, in the size of these things, etc.? Or what's the difference between a scone with different components? Of course, it had to be a scone because I'm not an Englishman and I think of England, I think of scones. So let's think of a hypothetical explanation, right? What happens if you put yeast in it or don't put yeast in it? Then what happens? It doesn't grow, it doesn't rise up, or it does. So then we can test this idea, because this is nothing but an idea. We need to test it scientifically. And we do that by doing a control. We do one without the component we are interested in, and one experiment with the component we are interested in. That is a design of a test. For example, we can take wheat or oatmeal, or we can baking powder or yeast. And then we do it, we test it, we collect the data, we evaluate our explanation and report that to the rest of the world. But it doesn't end there. You'll inevitably end up with other questions. And that is why it becomes an empirical cycle. There's so much to investigate about this Earth. It's so much more complicated than humans can comprehend. We can go on with this. It doesn't mean that science is useless, you should stop spending money about it. It means that we are learning stuff that's useful for us, and there's still more to learn. So here are my scones. On the top is an estuary without mud. It's a top image. The mud is colored orange in the middle one and the bottom one, where we feed increasingly more mud, and then look at the differences between these estuaries. And clearly the bottom one is much more filled, and the channel is much more funneled into a single channel as opposed to the top one. So mud has an important effect on how this landscape forms. Mud can be imported from the sea or from the river, it doesn't really matter, but it does that in the estuary. But then we know that estuaries also have real plants. We already saw that in this beautiful case in Wales. And this is how we put in the plants. We found a number of species that stay small enough as seedlings, and we simply feed them to the water and then give them a few days to grow and then start the tilting again and move on, and then again seed and give them a few days to grow, etc. So this is building really living landscapes. This is where rivers meet the sea and form these beautiful overgrown landscapes that capture the mud. You can see the brownish nutshell in between the plants. It's been captured. Here you can even see that the river banks are slightly higher, so they have more vegetation growing on it. And you can also see this is really the scale model. You can see the small plants, they still have their seed pods attached to them. But you can also see the black murky floodplains to the right and left. This is where peat formation has begun to form. It's beautiful. It didn't smell very nice, but it's really beautiful. So these are my scones, if you like, of a sandy estuary, one with vegetation only, one with mud only, and then vegetation and mud. All the permutations in one elevation map. And then we can study these in detail, which is precisely what we're doing now. We can also look at stratigraphy or sedimentology. What would this look like in an outcrop, or what would it look like in core data? So we core a lot of holes in the ground and see what's down there and then try to unravel what formed it, but we can do that in the experiment as well. So in the top you see our scans that's showing age of the deposit with the brighter colors on top because they're younger. And sometimes you see this little bit of a triangle pinching down. That's where the channel has carved itself. And then the bottom is a photograph where you can see what the mud layers look like if you carve a trench in the surface. So the top bit of that photograph is actually the surface, but then most of the picture is the trench. So we're looking at it horizontally. We're looking into the bed, into the deposits. You can also do that in the field. You can take a shovel with you or go to a river bank, and there you can actually see the old river deposits. And you see layers of sand and mud. We also drew that up here in brown and yellow. And some of this was taken, I think most of it has been taken in the Western Scheldt estuary in the southwest of the Netherlands. But you can find similar stuff in many places in East England. Of course, there's one remaining big challenge for our experiments. They're not only plants, they're also animals. You see the worms doing stuff to the mud here. There's this horizontal brown line where the mud has been changed in character and cohesivity by little worms. And there's also shells in it. How am I going to do this in the lab? I haven't figured it out yet, because the worms are far too big in scale to be taken out of the field. So I need something tiny that does a job. Anyway, if you have an idea, come and find a job in my institute. Right, so here we are, the living estuarine and deltaic landscapes of the planet. We can simulate much of that in a laboratory, and in fact you can simulate it and investigate it in many different. If you want to know more about it, we've got a couple of movies online that we made on the basis of our work. You can do your own storyline here, choose your own most interesting storyline, and do a couple of movies that are each not longer than about 3 minutes. And that is what I had to tell you. To summarize, what you can do now is play with water and sand. This is what scientists in our field actually do. Of course, we go about it scientifically with empirical cycle and control experiments, but the main thing is here to get a feeling of how the things work. And that feeling is very simple. Get a heap of sand, a watering can, and do the job. And then look at Google Maps or Google Earth and look for similarities and difference. But do mind the internet. There's a lot of rubbish out there. You can find crazy movies of rubbish explanations about rivers and deltas. That's it. Thank you for your attention.